All right, so now power in electromagnetic waves is all about this thing called the Poynting vector. I gotta say, Poynting had the most fortuitous possible name because what the Poynting vector does is, one, it points in the direction of energy flow. Otherwise known as the direction of propagation. And two, it says the power density of the wave. I'm going to tell you two different versions of the Poynting vector. There is a time domain expression for it and a time average expression for it. And the time average expression you get using the phasor quantities, but you can also get it using the time domain quantities. It's just easier in phasor domain. So, time domain first. The Poynting vector, for which we use the symbol S as a function of time, is the electric field as a function of time cross the magnetic field as a function of time. So that is at a point the power density of the wave. So it's got units of watts per meter squared, which makes sense because the electric field has units of volts per meter and the magnetic field has units of amps per meter. Those things don't really make any sense until you cross them and get the Poynting vector. So this is the instantaneous Poynting vector. Now, if you want the phasor domain version of this, there's not really a phasor of the Poynting vector, and you'll see why in a second. But if you want the time average Poynting vector, then we have S average, which is equal to 1/2 the real part of the phasor electric field crossed with the complex conjugate of the phasor magnetic field. This is the time average power density of this electromagnetic wave. What is the Poynting vector good for? It can tell you some important things. In particular, it can tell you how much energy is flowing through here. If you have a waveguide, you can do a flux integral across the cross-sectional area of the waveguide to find out how much power is flowing down that waveguide. If you have a transmission line, you can do a flux integral across the cross-sectional area of that transmission line to figure out how much power is flowing down that transmission line. And interestingly enough, if you have an antenna that's radiating, like antennas do, you can surround that antenna with a sphere and do a flux integral of the Poynting vector over that entire sphere and find the total power radiated by that antenna. The way you do that is whatever power you're trying to calculate is equal to the integral over that surface of the Poynting vector dot the surface normal vector. I'm going to use dA instead of ds because I don't want to confuse the Poynting vector with the surface normal differential element. So this one is the Poynting vector. That's the differential surface element. And that's what the Poynting vector does. Another interesting An important fact about the pointing vector is if you have a pointing vector and you're talking about how to spell pointing vector, if you are talking about power flow in lossy media, you know that the electric field in a lossy medium has a form kind of like this, where it's got an amplitude and it's got an e to the minus j beta z and an e to the minus alpha z, right? And your magnetic field, if it's a plane wave, your magnetic field has an amplitude that's like this, and e to the minus j beta z and e to the minus alpha z like that. And the electric field is in some direction. Let's say it's in the, we'll make it the x direction. And the magnetic field is in the y direction. So when you cross them, you get something that's in the z direction. So that's cool. But since the pointing vector, the time average pointing vector, is 1/2 the real part of E cross the complex conjugate of H, the phase accumulation on here goes away. We're not going to have any complex part of our time average pointing vector. We're just going to get a real number, which makes sense. The amount of power, like the net power flow carried by this wave, isn't going to be time varying, even though the instantaneous power flow does vary with time. So what we get for this pointing vector is z hat E naught, I'm going to take its magnitude because it might be a complex number, squared, divided by eta, e to the minus 2 alpha z. So notice each of our fields falls off as e to the minus alpha z, but the power density of the wave decays with a factor of 2 on that attenuation constant. All right, now the activity for today that I want you guys to try out is an example about plane waves in lossy media, about seawater. So the conductivity of seawater is about 4 Siemens per meter, and its relative permittivity is about 80. So the question is, what's the maximum frequency at which seawater is a good conductor? And what's the minimum frequency at which it's a good dielectric? And lastly, what is the attenuation? Well, not the attenuation constant, but what is like P out over P in attenuation for 10 meters of seawater at 60 kilohertz. Have a good time with that. Post your answers on the discussion board, and I will talk to you there.